This is lecture 31 of the subject analog circuits. In this class, I am going to discuss active band reject filter and introduction to power amplifiers. So, the contents are wide band reject filter, narrow band reject filter and power amplifiers. So, before starting the active band reject filter, let us go through with the active band pass filter, which I had discussed in the last class. So, in case of active band pass filter, when we draw the frequency response, then the responses, that is in between gain and frequency, the response is like this. Fine. So, active band pass filter which passes a particular band of frequency and rejects the remaining frequency. And there are two cutoff frequencies, one is FL and another one is FH. Fine. This FL is the lower cutoff frequency, FH is the higher cutoff frequency, and this is the maximum gain which we are getting, let us say it is AF. So, in active band pass filter, FH is greater than FL, FH is greater than FL, and this is your pass band, this one is stop band, this one is stop band, because signal is attenuating in stop band, right. What happens in active band reject filter? This active band reject filter that is also called band elimination filter, band stop filter. So, for active band reject filter, when we draw the frequency response, that is the graph between gain, that is the voltage gain versus frequency, then the response is like this. And in active band reject filter, we can see that this is your pass band, this is your pass band and this one is stop band. So, band reject filter is the filter which rejects a particular band of frequencies. Rejection means in that particular band the gain will be very less, gain is very less means signal is getting attenuated, fine. So, in this case the cutoff frequency, this is FH and this one is FL, right. So, we can see that in active band reject filter FH is less than FL, fine. So, we have to be very careful while designing the band pass filter and band reject filter, because to design wide band pass filter and to design a wide band reject filter, we need first order high pass filter and first order low pass filter, and we all are already familiar with first order low pass filter and first order high pass filter. We had derived the expression of the cutoff frequency FL and FH for the high pass and low pass filters, fine. So, while designing the band pass filter, that FH should be greater than FL, and in band reject filter vice versa, and we can see from these graphs. Now, how we design this band pass and band reject filters? So, designing of band pass filter is already covered. To design band pass filter, wide band pass filter, we cascade the first order high pass filter with first order low pass filter, but in case of wide band reject filter, we add the response of the high pass filter and low pass filter. When we are using the word addition, it means that we need an adder circuit, we need a summer circuit in designing of wide band reject filter. So, designing of wide band reject filter is, firstly we take a first order high pass filter. We all are familiar with first order high pass filter. We take a first order low pass filter. and we apply the same input signal at the first order high pass and first order low pass filter. Then let us say we are getting the output voltage VO1 from the first order high pass filter and the output voltage VO2 from the first order low pass filter. Then we add this VO1 and VO2 with the help of adder circuit, and finally we get the output V naught. And when we draw the graph of V naught upon Vin for this particular configuration, then we get the frequency response of the wide band reject filter. So, this is the basic block diagram of wide band reject filter. Now, for wide band reject filter, as I have already discussed, the low cutoff frequency FL of the high pass filter must be larger than the high cutoff frequency of FH of the low pass filter. It means that FL should be greater than FH in case of wide band reject filter, and the pass band gain of both the high pass and low pass section should be equal. And what about the roll off rate? What about the roll off rate for wide band reject filter? So, the roll off rate for wide band reject filter is, we can see that this is minus 20 dB per decade, and this one is plus 20 dB per decade, fine. And I have already mentioned the FH and FL, that is the cutoff frequency. These cutoff frequencies are also called minus 3 dB frequency, corner frequency, break frequency. So, again in wide band reject filter we need two cutoff frequencies, one is lower cutoff frequency and another one is the upper cutoff frequency. So, coming to the circuit diagram of the wide band reject filter. So, we can see that this op amp A1, it constitutes the first order high pass filter. So, we have already designed this first order high pass filter, fine. This R and C, it provides the filter function, R1 and RF, it provides the gain, and this A2 op amp, it constitutes the first order low pass filter, fine. And what we are doing, let us say the output of first order high pass filter is VO1 and the output of the first order low pass filter is VO2, and we are just adding this VO1 and VO2 with the help of summer circuit. So, this A3 op amp is the summer circuit. So, I had explained it in the earlier classes, in the class when I was discussing the applications of the inverting configuration. So, one of the application of the inverting configuration is the adder circuit, summer circuit, fine. So, in the adder circuit what happens, if we need to add two signals, two voltages V1 and V2, let us say V1 and V2, then we apply this V1 and V2 at two resistors, and these two resistors are connected to the inverting configuration, and of course, there is a negative feedback. This is resistance RF, this one is R1, this is R2, this is output voltage V naught. So, this is your adder circuit. From here when we calculate V naught, then it is equal to minus of RF upon R1 into V1 plus RF upon R2 into V2. Minus sign is coming because this is the inverting configuration, fine. And if we want V naught is equal to minus of V1 plus V2, then what we do? We take RF is equal to R1 is equal to R2. So, in this circuit we can see that these R1, R2, RF are replaced with R2, R3, R4, and the values of all three resistors R2, R3, R4 are same, that is 10 kilo ohm. It means that the output voltage V naught, it will be equal to minus of VO1 plus VO2. the two voltages will be added, but the minus sign will come because of this inverting configuration of A3 op amp. So, don't get confused with the minus sign just represents that the output is 180 degree out of phase with input, fine. So, to design wide band reject filter, we need 3 op amps, A1, A2, A3. A1 that is the first order high pass filter, A2 that is the first order low pass filter, and A3 that is the summer circuit, and the design steps are same. We all are familiar with the design steps. To design the wide band reject filter, again firstly we will design the first order high pass filter to get a particular cutoff frequency FL. Then we design the first order low pass filter to get the particular cutoff frequency FH, and of course this is wide band reject filter. Then in this case the FL should be greater than FH, fine. So, we can separately design this first order low pass and first order high pass to get a particular FL and FH, and after that just add a summer circuit and just take the values of all resistors same, R2 equal to R3 equal to R4, because when we take these resistors same, then we get V0 is equal to minus of VO1 plus VO2. So, the two voltages will be added, fine. So, this is about the wide band reject filter. Now, coming to the narrow band reject filter, that is also called notch filter. So, this notch filter, that is a narrow band reject filter, it is designed using twin T networks. Twin T network. What is this twin T network? Because we use two T networks. In one T network, there are two resistors and one capacitor, and another T network, there are two capacitors and one resistor, right. So, we can see that there are two resistors, one capacitors, two capacitors, one resistors. So, this is your twin T network. If we only use twin T network, then it is the passive notch filter, and when we apply the response of this twin T network at the non-inverting configuration of the op amp, means we are using this op amp, then it becomes active notch filter, right. And you can see that this op amp, it is in non-inverting configuration and it is just the voltage buffer. You can see that the inverting terminal, it is connected to the output, there is no feedback resistor. So, it is a voltage follower, it is in voltage follower. So, this is the application of non-inverting configuration, and the advantage of this non-inverting configuration is it provides high input resistance. So, loading effect is very less, that is the advantage of the active notch filter over passive notch filter. So, the point is that we can design this notch filter without this op amp just by using twin T network, but obviously that will be the passive notch filter and there will be loading effect, the signal will be attenuated, right. So, the concept of this notch filter is it is used to reject a single frequency. Like in wide band reject filter, it rejects a particular band of frequency, but this narrow band reject filter, that is notch filter, it rejects a single frequency. And the most common use of notch filters is in communication and the biomedical instruments for eliminating undesired frequencies, because if we know that at a particular frequency there is a lot of noise. So, we want to reject that particular frequency. So, for that we can use the notch filter, and when we draw the frequency response of the notch filter, that frequency response, that is the voltage gain versus frequency, that frequency response is this one. This frequency is called Fn. You can see that at the frequency Fn, the gain is minimum, means the signal is getting attenuated at the frequency Fn. This Fn is called notch out frequency. This Fn is called notch out frequency, and for this notch filter, this notch out frequency Fn is equal to 1 upon 2 pi RC, 1 upon 2 pi RC, where R and C are the resistor and capacitor that is connected in the circuit. So, it means that if we want to reject a 50 hertz signal or 100 hertz signal, right, then that 100 hertz signal is your notch out frequency Fn. So, Fn is given, which frequency we have to remove, it is given. Now, we have to find out the value of R and C just to reject this Fn frequency. Again the concept is same, Fn is given, one equation, two unknown R and C. Again we will take C less than or equal to 1 microfarad, and corresponding to this C, let us say C can be taken as 0.1 microfarad, 0.01 microfarad, any value. Corresponding to this C and Fn we will get some value of R. Just put these values of R and C in this circuit, then it will reject that particular frequency. So, this is the design methodology for notch filter. So, it is very easy, in fact, very straightforward, fine. So, this is about the narrow band reject filter, that is notch filter. Now, one more thing I want to mention here is higher order filters, like in low pass and high pass filters, we have studied the first order and second order filters, right. If we want to design third order low pass filter or third order high pass filter, so what we can do, we can just cascade the first order and second order, then it becomes the third order. It means that to design the third order low pass filter, just take a first order low pass filter and cascade it with the second order low pass filter. This is input signal V in, this is output signal V naught. So, it becomes third order low pass filter. Similarly, if we want to design fourth order low pass filter, then we need to cascade two second order filters. When we cascade two second order filters, then it becomes fourth order. So, we can design any filter of any order, but as the order of the filter increases, then you can see that the complexity also increases, because the number of components will increase. So, accuracy declines, but the advantage of using the higher order filter is when we draw the gain versus frequency response. Let us take the example of low pass filter. Let us say this is for first order filter and the roll off rate is minus 20 dB per decade, right. And when we use second order filter, second order low pass, then the roll off rate is minus 40 dB per decade. Similarly, for third order, the roll off rate will be minus 60 dB per decade. For nth order filter, the roll off rate will be minus n into 20 dB per decade. So, as the order of the filter is increasing, the roll off rate is increasing. So, your stop band response, it moves towards the ideal stop band response. The actual stop band response, it moves towards the ideal stop band response. What is the ideal band stop response? This one is ideal band pass. In ideal stop band response, there is no gain, signal is completely attenuated in the stop band, right. And you can see that as the order of the filter is increasing, your actual stop band response is moving towards ideal stop band response. That is the advantage of the higher order filter, but at the same time we need extra components, we need more components. So, accuracy is the problem, because when we theoretically calculate some value of resistor and when we practically design that circuit on breadboard in the lab, so there is a difference, because we cannot take the actual value of the resistor, because there is some tolerance of 5%, 10%, 20%. So, there is some variation in the component values. That variation may be due to the temperature also, fine. So, due to these things when we calculate values theoretically and when we design the circuit in the breadboard practically, right. So, there is some difference because of these variation in the component values, fine. So, just the point is that higher order filters it can be designed with the help of first order and second order filter. That is why we are more focusing on first and second order filter, because with the help of first and second order filter we can design third order filter, fourth order, fifth order, nth order filter we can design with the help of first and second order filters. Now, coming to the next topic, that is power amplifiers. Now, what is the difference between this power amplifier and the small signal amplifiers which we have already studied? A small signal amplifier means, like in MOSFET we have studied common source, common gate, common drain. In BJT we have studied common emitter, common base, common collector. These are the small signal amplifiers that we have already studied. In small signal amplifiers, the voltage and current swings are small and it is basically used for data processing and signal processing. And this small signal amplifiers, it provides very limited power at the output, but after signal processing we need power at the output. We need in fact a lot of power at the output. The reason is that output of the amplifier is connected to some output device. That output device, it may be motor, it may be printer, it may be any public address system, right. So, we need a large of power at the output and we cannot generate such power, such large power with the help of small signal amplifiers. So, what we do, we connect the last stage of any amplifier as the power amplifier, last stage or last two stages as per the need, as per the requirement of the power. So, this power amplifier, it provides a lot of power, and the classifications of the power amplifier, it is based on for what portion of the input signal the conduction current flows in the output, for what portion of the input signal the conduction current flows in the output. On this basis the power amplifiers are classified, but for small signal amplifiers, we have already seen this small signal amplifiers, there is a complete signal at the output which is the replica of the input signal in the amplified form. So, these things I had discussed already in small signal amplifiers, like if we are giving this sine wave at the input. So, we get the amplified version of this sine wave at the output. So, the shape of the signal is same, it should be same. If the shape is changing after amplification, it means that there is distortion, there is distortion. So, that is why we need linear amplifiers, but this is the story of the small signal amplifiers. But in power amplifiers, these amplifiers are classified on the basis that for what portion of the input we are getting the output, that is we are taking here the conduction current, that is in the case of BJT it is a collector current at the output, fine. So, there are mainly 4 types of power amplifiers. In general, these are the main types of power amplifiers: class A, class B, class AB and class C power amplifiers. Now, starting with the class A power amplifier. In class A amplifier, we bias the transistor in such a way that the output current flows for the whole input cycle. If the output current is flowing for the whole input cycle, it means that the conduction angle is 360 degree. One cycle means 360 degree. For complete 360 degree, the output current is flowing. That output current is that output current is the collector current. So, this is the collector current waveform for the class A amplifier, and for you can see that for the whole cycle 360 degree, the output current is flowing, collector current is flowing, and but the efficiency of this class A amplifier is very less, it is only 25%. Next is class B amplifier. In class B amplifier, the conduction angle is 180 degree. If the conduction angle is 180 degree, it means that only the half cycle of the input, the output current is flowing. So, this class B amplifier, pure class B power amplifier, it gives distortion. Obviously, we will get distortion because only for the half cycle we are getting the output. There will be distortion, but the efficiency is more than 75%. In general, the maximum efficiency which we get is 78% for class B power amplifiers, and this is the collector current waveform for class B amplifier. We can see that the output current, that is the collector current, is flowing only for the half cycle, only for from 0 to pi. Next is class AB power amplifier. It is used in push pull configuration, that is the first point, and the conduction angle is slightly higher than 180 degree, but efficiency is slightly lower than class B power amplifier, but the biggest advantage of class AB amplifier is the output of the class AB is distortion free. That is one of the biggest advantage of class AB amplifier. That is why in many cases we use this class AB power amplifier, because it is distortion free and we are getting the efficiency just slightly lower than the class B power amplifier. Next is class C power amplifier. In class C power amplifier, the conduction angle is very much less than 180 degree, but the efficiency is around 95%, and for class C power amplifier the efficiency is highest, it is 95%, and it is basically used in radio and TV signals. Basically, since the conduction angle is very much less than it is very lesser than 180 degrees, so we get sharp pulses, right, and it is used as the carrier waves in radio and TV signals. That is very much required there, because the efficiency is a very major factor in the transmission of radio and TV signals. That is why we use class C amplifier there, because the efficiency is highest 95%, and the lowest efficiency we are getting from class A power amplifier, that is 25%. And this one is the collector current waveform. We can see that the conduction angle is much less than 180 degree. These are the references.